Hello everybody, welcome to Free Coder. Here you can learn all about programming.
So, if you're a developer, chances are you're building something with a large language model right now. But let's be honest, for a lot of us, what's happening under the hood is kind of a black box. I'm talking about the most fundamental piece of the puzzle, the token. It's time we demystified that.
All right, let's kick things off with a problem that you've almost certainly run into, maybe without even realizing it. It's a little mystery that has a real impact on your wallet and your model's performance.
Picture this. You send the exact same prompt, same words, same everything to two different AI models, but you get back two totally different bills. How is that even possible? It all comes down to the number of tokens. But wait, how can the same words result in a different number of tokens?
And I mean, look at this. It's not a small difference. For a simple hello world, Anthropic's model rings up 11 input tokens. Google's just 4. That is nearly 3 times more tokens for the exact same 2 words. This isn't some weird bug either. This is completely by design.
So, to figure this out, we have to get down to the one thing that every single one of these models runs on. It's not words, it's not even characters, it's something else.
And that brings us to the core idea you need to remember. Tokens are the currency of LLMs. That's the perfect way to think about it. Every time you send text in, you're spending tokens. Every time the model sends text back out, you're spending tokens. It's the entire economy of the system.
So what is this currency really? Well, a token is just a chunk of text that the model's been trained to recognize. It might be a whole word like hello, or just a piece of a word like ing, or sometimes just a single character. The important part is that each of these unique chunks gets mapped to a number. And here's how it fits into the whole flow. You type your prompt in plain English, right? But the very first thing that happens is that text gets chopped up and encoded into a list of numbers. Those are your tokens. The LLM does all its magic, all its thinking, using only those numbers. It never actually sees your words. Then it generates its response as another list of numbers, which finally gets decoded back into the text that you read. Okay, now that we have that foundation, we can finally crack our original case. Why did Hello World cost 11 tokens on one model, but only 4 on another? The answer, it turns out, is surprisingly simple.
It's all about the vocabulary. You can think of it like this. Every model provider, OpenAI, Google, Anthropic, trains their own unique tokenizer. And each tokenizer has its own special dictionary of these text chunks it knows. Anthropic's dictionary is just different from Google's, plain and simple. Let's actually see how that works. The tokenizer gets your text, hello world, and it greedily looks for the biggest chunks it recognizes from its vocabulary. So for a model like GPT-4, it might see hello, then world with the space, and then 1. It finds those 3 chunks, looks up their corresponding numbers in its dictionary, and boom, that's your token array.
And this isn't just some abstract idea. It's literally code you can run. You can grab a library like TickToken, call the encode function on a string, and you'll get back that exact array of numbers. The whole process of turning our language into the machine's language is just a function call away.
Okay, so if every model has its own vocabulary, that begs the next question, right? How are these things even built? Understanding this is the key to why they're all so different. Well, the most basic way you could do it is with a character tokenizer. It's exactly what it sounds like. Every single character gets to be its own token. C is a token, A is a token, T is a token. It's super simple to build, but man is it inefficient. And you can see that inefficiency right here. With a character tokenizer, the phrase cat sat mat, 11 characters, becomes 11 separate tokens. But a smarter subword tokenizer can represent that same phrase in just 8 tokens. And fewer tokens always means less work for the LLM and, a smaller bill for you. So how do these subword tokenizers work their magic? Well, they're trained on huge amounts of text, and they basically learn to spot patterns. They find the groups of characters that show up together all the time, like th, or ing, or sta, and they turn those common groups into their own efficient single tokens. And this gets us to the real heart of it. Building one of these vocabularies isn't just a technical exercise. It's a strategic decision. It involves a massive trade-off that every single model provider has to wrestle with.
Here's the deal. You can have a small vocabulary, which is great because it doesn't take up much memory, making the model smaller. But the downside is it's inefficient. A big word like understanding might have to be broken into 5 separate little tokens. On the other hand, you could have a massive vocabulary. Now you're super efficient.
Understanding might just be 2 tokens. But that vocabulary list itself is huge, which makes the model bigger and hungrier for memory.
This also totally explains what happens when you use a weird or rare word. Take a word like frabjous from the Jabberwocky poem. The tokenizer's probably never seen it, so it's not in the vocabulary. The only thing it can do is break it down into smaller pieces it does recognize. In this case, frabjous becomes 4 different tokens, which is way less efficient.
So why should you, as a developer, actually care about any of this? Well, for one, if you're working with a language, spoken or programming, that wasn't a huge part of the training data, your prompts are going to use more tokens and cost you more money. That's why sending JavaScript code is more token efficient than sending, say, Haskell. At the end of the day, getting a handle on this helps you write way more efficient prompts and actually predict what your build is going to be.
So let's just put it all together one last time. Your text gets encoded into numbers, the LLM does its work on those numbers, it outputs a new set of numbers, and those numbers get decoded back into text. The key takeaway is that from the model's point of view, it's tokens all the way down.
And that's a wrap. You now know that tokens are the currency of these models, that every model has its own unique vocabulary, and that this leads to some really important trade-offs in efficiency and cost. So I'll leave you with a question. Now that you know all this, how are you going to change the way you write your prompts and build your apps?